So this is the third part of my forces notes, and we're going to look at Newton's third law. Before we begin, go ahead and ask yourself these questions and just pause it. See if you can come up with the answer. Okay, you should have paused it by now, but if you didn't, you're still going to see the answer. What's Newton's first law? The law of inertia, and that's talking about when there's an object in motion, it's going to stay in motion, and when there's an object at rest, it's going to stay at rest unless acted upon by an outside force. Second law was best stated in an equation. Force causes acceleration, but mass is going to get in the way. If there's more mass, there's going to be less acceleration. If there's less mass, there's going to be more acceleration. But force results in acceleration in the same direction. Net force equals mass times acceleration. In an object like this, I went ahead and gave you the net force because this object would have had weight pushing down. This object would have had normal force going up. These would have been the same. These would have canceled out, leaving you with this net force. And so this is what's going into that equation, causing the acceleration, but it's going to depend on the mass. Remember, mass is kilograms. And so when you rearrange F equals ma, divide out m, cross out m, a equals F over m, which is that. Plug in the numbers, and you get 2 meters per second squared. And in whatever direction, in this case, it would have been to the right. To be perfectly correct, you need to have the direction when you know the direction. Here's a question related to Newton's third law, and sometimes it seems a bit misleading because they'll usually in a question show you something like this. You have a bug coming out a window, and it gets squished. So, which one does a car or butterfly exert more force in the collision? And the key here is knowing Newton's third law. The actual force of the butterflies, we'll go back to that slide again right here. That force right there, these are going to be equal. The butterfly exerts the exact same amount of force on the car as a car exerts on the butterfly. The problem is that the butterfly's mass is a whole lot less. So therefore, it's going to decelerate much quicker, and therefore you see the squish. So let's take a look closer at the law. Mathematically stating, the force of one is equal to the force of the other, but mathematically stating also, there's a negative, which means opposite direction. So if one force, if this guy's pushing that cart with 20 newtons to the right, the cart is pushing the guy with 20 newtons to the left. Forces always occur in pairs. So when I talk about pairs, I'm talking about two objects. This is going to be very important for Newton's third law. You are going to be looking for two objects in any question. It's objects. There you go. Very poorly spelled, but two objects. So here you have a cart and a person both feeling equal and opposite forces, and then based on their masses, they might have a different acceleration that results. But the forces are always going to be the same, equal in strength, opposite in direction. Different masses result in different accelerations. That's where this slide starts. And so let's take a look. The equivalent of force, just remember F equals ma. So we have two objects and two forces. You have the ma of 1 and the ma of 2. But the opposite of it, figure out which one you want to call object 1, figure out what you want to call object 2, and this equation right here becomes that equation right there. Okay, so the reason why, so if the forces are the same, but this person, well in this case the cart's mass is less, the acceleration that's going to result from having less mass, since this is the same, is going to be greater. So we can look at Newton's second law, F equals ma, and we can rearrange it to kind of analyze what happens to acceleration. And I like to plug in numbers. Let's pretend this is 1 and this is 1. So force over mass. If I take mass and I make it 2, I just went ahead and made acceleration less. I took it from 1 over 1, which is 1, to 1/2. So the higher this goes, the lower this goes. So mass and acceleration are inversely related. Bigger masses get less acceleration out of the same forces. Okay, so let's try a couple problems. And we're going to start off with, this is more of Newton's second law, and then we'll do a Newton's third law problem, but they're all related. The key here, when you're doing Newton's second law, well actually that's before we get into Newton's second law, the next one's a math problem with Newton's second law. Here's just a general question. What is the force felt by Bob in what direction when he pushes his cart with a force of 20 newtons to the right? And the force on Bob is going to be 20 newtons to the left. And so equal and opposite forces, that's the reason why this is the answer. So 20 newtons to the left. Now we have 20 newtons to the left. This is a given in this problem. Now what is the acceleration of the cart? So this is a Newton's Newton's second law problem. Not Newton's third law where we're carrying about two objects. The key here is we're only worried about the cart. So ignore everything else. We're just looking at the cart and we're looking at the net force on the cart. So just ignore all this stuff. This is why it's Newton's second law. We're only concerned with what's happening to this cart. This is why it's Newton's second law, which is Fnet equals ma. And we'll arrange that for A equals Fnet over m. And since there's only one force, that is your net force here. And so to figure out this acceleration, we're just going to take the force, once again, of the cart, 20 to the right, 20 newtons to the right. And we're going to take that mass, 5 kilograms, and we get our answer, and it's going to be 4 meters per second squared. So these are all derived units. So these would cancel themselves out and become meters per second squared, and the answer would be to the right. So what's the acceleration of the cart? 4 meters per second squared to the right. Once again, I wasn't concerned with anything going on here. I was only concerned with the cart's mass, the cart's force, and the cart's acceleration that resulted. So that's why it's Newton's second law. Same thing here. Now we're just looking at Bob. What is the acceleration? Not concerning with anything else. Only one object in this problem. Fnet equals mass times acceleration. Acceleration is Fnet. Once again, only one force here, and it's the same as the cart because of the third law, but that's not the equation. We're not going to be using the third law equation. I'm using the second law equation because we're only concerned with what's happening to it's Bob over here. And so you have the mass, and to do this, so you have a net force felt on Bob of 20 newtons to the left. You have a mass of Bob of 50 kilograms. And when you solve all that, you are going to get an answer of 20 divided by 50, and you get 0.4, and it's acceleration, so meters per second, and then to the left. Force, net force, is in the same direction as the acceleration. In this case, we're just concerned with Bob. That's why it's Newton's second law and not Newton's third law, which is that ma1 equals ma2, but in the opposite direction. Okay, now this, we have 95 kilogram Joe. So let's go ahead and draw Joe right here. And he's on a skateboard. There we go. Skateboard right there. And he's going to jump off to the right. So he's going to jump off to the right. And when he jumps off to the right, Joe is going to accelerate at 1.5 meters per second squared. And he's 95 kilograms. And he's standing on a skateboard, which is 0.8 kilograms. And we're concerned with what is this going to be? And once again, we know it's going to be the opposite direction. And this turns into a Newton's second law, because in this problem, we're going to be using Joe's mass and the skateboard's mass and Joe's acceleration to find this acceleration. So in order to do these, and here's your equation, we have to determine which one we want to call 1, first of all. Let's go ahead and call Joe 1. Let's go ahead and call skateboard 2. So we're going to have, this is an equal sign right here. We have the acceleration and mass of Joe. So here's all Joe's information. And here's the skateboard. So we're going to call that 2. And so we have Joe, which has a mass of 95 kilograms, an acceleration of 1.5 meters per second squared to the right. And then the mass of the skateboard is 0.8 kilograms. And the acceleration is unknown, but we know at the end it's going to be to the left as a result. So we just plug and chug from there. 95 kilograms times 1.5 meters per second squared. So once again, I didn't leave off the units for the math, but we're just doing this up here, equals negative. If you forget the negative, you should know that this acceleration is going to be in the opposite direction. And if you do forget the negative, it's easy to do. Just remember at the very end, it's going to be the opposite direction. You know that that's going to be the fact every single time. 0.8 kilograms and we're trying to find the acceleration on the skateboard, which we call object 2. This is just a subscript, just represents the acceleration of the second object. Once again, Newton's third law, because we have two objects interacting with each other, and we're concerned with two objects in the net result. So if you do this, you have negative 0.8, negative 0.8. These cancel out. Acceleration's on the top. It's not below. It's not in the denominator. So when we solve for this, we solve for the acceleration of 2, in this case, the acceleration of the skateboard. So we take 95 times 1.5 equals divided by a negative 0.8, and we get negative 178.125. And that's going to be meters per second squared. Now we want to finalize that answer. 178 point, let's just go ahead and round it to 178 meters per second squared. And this is going to be to the left. Once again, this negative symbol right here turned into left in our final answer. Okay, so now we can revert to another question. Does the Earth or the bug feel a greater force of gravity? So what's happening here is the Earth is pulling the bug down, but the bug is also pulling the Earth up. How would those forces compare? Go ahead and pause it, think about it, and then go to the next slide. Okay, related to Newton's third law again. Once again, the Earth is massive, so the accelerations are going to be different. But the force of the bug, and once again, this is going to be force of gravity, force of gravity. In reality, this is the same as the weight of an object. When you're only concerned with the object and what's going on with that, this would be the FW equals mg if I was ever trying to figure out some sort of math with that. But Fg is going to be equal to that. It was a previous lesson. But the force on each of these is going to be the exact same. Earth is pulling on the bug as much as a bug is pulling up on the Earth. And the net result, though, is because of the mass being so small, the acceleration is going to be much bigger for this bug over here.